I've known Kristen for over a decade. He's definitely one of the world leaders in understanding the climate and circulation and atmospheric dynamics of extrasolar planetary systems. And it's a great pleasure to have him here today. He's a professor at University of Toronto and the director of their Center for Planetary Sciences. Thanks, Kristen.
Thank you, John. Can you hear me? So I'm going to try to describe to you a number of things about the atmospheric circulations of exoplanets and how we study this circulation. And Jonathan tells me that there is an hour plus 20 minutes for questions. So what I'm trying to be pedagogical here. So I invite you to interrupt me and ask questions in the middle, and then we go along. I think that's the best way to do it. I thought I would organize these 3 lectures in the following way. Today, and maybe if we're not done a little bit more tomorrow, I wanted to go over general principles of what drives circulations and a number of key aspects that are important to understand how circulation works, and a very brief discussion of methods of solutions, how we get to solve the equation that we believe are relevant for atmospheric circulation. So it's a lot of basic principles and fluid dynamics today. Then the next lecture, and maybe it's going to go beyond the lecture 2, is actually a discussion of a sort of a survey of applications of these principles. And by that I mean a discussion of what people have been able to do on the problem of the hot Jupiter circulation regime, warm mini Neptunes, and then discussion of the climate of exotic version of Earth, I guess is what I want to try to cover. And then the third lecture might be finishing with the application part, and I want to, I guess, offer you a discussion of sort of some of what I think is one of the most interesting aspects of what's happening here, the fact that because we're looking at the atmospheric circulation in planets that are beyond the solar system, there is still room for new physics to actually emerge as important in these atmospheres. And I think we're not done with finding all the key physics ingredients that will matter. I'll give you some examples of that, and then a combination with some open problems, some things that we know we're not doing well, and there is room for a lot of improvement there. So that's sort of the plan I have. The other thing I should say that I come from I have an astrophysics background. So this is sort of the bias you'll see in this presentation. There's, of course, a lot of literature of non-atmospheric dynamics in planetary science. And sometimes it can be a bit daunting, and it's not an easy literature to dig through. So I try to adopt the point of view I'm comfortable with and provide insight into what I think makes sense from the point of view of maybe a fluid dynamicist. And hopefully people will find that useful. And maybe the first thing I should address is why circulation matters. It's not a stupid question, because there are actually a number of cases where you can do a very good job at describing an atmosphere without worrying too much about the atmospheric circulations. So in the limit of, for instance, a very thin atmosphere, imagine a terrestrial planet with a thin atmosphere, something that in the limit of an airless body, we heard about this term yesterday, then there will be an atmosphere, there will be atmospheric motion, but the atmosphere is thin, transparent, and so basically the system from the point of view of an observer and an astronomer, it will behave like a ball of rock. So that's one example of where you might not want to care too much about the atmospheric circulation. There are also cases where in the limit where the atmosphere is very deep, actually sort of somewhat counterintuitively, if you will, the atmospheric circulation is very efficient at equalizing temperature on the planet. A good example of this might be Venus, for instance. If you care about what's going on near the surface on Venus, under 100 bar of CO2, you find that the atmosphere is very good at actually equalizing temperature there. And you'll do a good job at just doing a one-dimensional relative convective description of the atmosphere there without worrying about detail of atmospheric circulation. So there are limits in which you might not want to care too much about atmospheric circulations. But in many cases, atmospheric circulation will play an important role in determining some of the emergent properties of the planet or the exoplanet. So a good example of this I think, is the Earth. What you're seeing here is the Earth's latitudinal relative energy budget. So it's an average over latitude circle of the energy flux received by the Earth and emitted by the Earth. And you want to think about this as top of the atmosphere. So this can be actually measured accurately with satellites. And so the blue curve here is what the Earth receives as a function of latitude from the North Pole to the equator to the South Pole. And the units of the flux are watts per square meters. And then the red curve is what you can measure from satellites looking at the Earth, what is radiated in the infrared by the atmosphere and the ground, so what comes out to space. And of course, the Earth is in radiative equilibrium to a good approximation. There's some seasonal variation there that you might want to count, but to a good approximation, what comes in, well, certainly over a year it's the case. So for the sake of the argument here, the two are actually equal. Globally, what comes in comes out, but actually locally that's not the case. And that's where circulation is important. So you see what comes in at the equator is more, in excess of 300 watts per square meter, is more than what comes out in the infrared at the equator. And what comes out towards the pole is more than actually what is received. And that is the action, the combined action on the Earth of mostly the atmosphere and to some extent the oceans. That actually the Earth receives more insolation at the equator, less at the pole, and the atmosphere and the ocean have a tendency to equalize that, to basically bring the heat away from the equator towards the cooler regions at the pole. And so that's what all atmospheres tend to want to do, actually, as you'll see. We'll discuss more generally. And so depending on your point of view, that's important or not. So you see, if you look at the pole, if you were to treat the Earth as a purely radiative body, like neglecting the atmosphere, or actually accounting even for the atmosphere, but saying there is no atmospheric motion, you could do that even better. Like various columns of gas, but without motion. You could make a mistake that is of order maybe something like, 20% here at the equator. Now 20% error in the fluxes and then the related errors in the temperatures might not be so bad for an astronomer. When we look at exoplanets, I don't think we are aiming at doing better at the moment than 10% sort of inferences on fluxes and temperature profiles and wind profiles. That's actually pretty good if we can get it right.
That's misleading because if you have the tropics within that depth force, you get a runaway signal. So you have the order of magnitude.
Okay, so maybe it's even worse, yeah. And the point I was just trying to make here that now if you were to look at the Earth and focus about the pole, now this same atmospheric circulation plus ocean transport here can get you wrong by a factor of 3. So I'm just trying to illustrate here that actually why circulation matters. Basically, what you see in the infrared, which we will hear a lot more about, I think from Jacob Beam, we tend to look at exoplanets in the infrared. What you see in the infrared is actually a combination of what's received, the radiation part of the problem, and the fact that the atmosphere will redistribute heat, and after that you irradiate. It's a combination of these two processes, and so what you see as an astronomer can be strongly modulated by circulation. So I think that's why circulation matters. Let's stay with the Earth for a little bit. This is a nice picture of the Earth's atmosphere. I'm not sure even it's true color, but it might be true color. And then the just simple point I want to illustrate here is that you get a feeling right away, if you think about it that way, you get a feeling that given this very weak radius of curvature here and the thinest of the atmosphere, if you want to fit a hurricane size features, structure of the moving atmospheric flow in that atmosphere, it has to behave in 2 dimensions, basically. It's so thin relative to actually the horizontal extent that any large-scale structure you want to fit here has to behave in a quasi-2-dimensional way. And so that's one of the things that we'll get to discuss in more detail. So how can we start in trying to understand, just really going to the basics, trying to understand how to describe this atmosphere? Well, a simple definition might be that we are looking at a thin layer of fluid of finite mass, and that layer of fluid is exchanging momentum and energy with its boundaries. And what I mean by that, in this case, it would be the surface at the lower boundary and space as the outer boundary. And so that's basically what we are after. And the issue of the finite mass and whether that constant I'll address a little bit later. What sorts of tools of physics we want to use and invoke to actually describe that atmosphere? It's a collisional fluid. So what I'm dealing with here are collisional atmospheres, not exospheres that we heard about. They are interesting by itself, but all of what I'm discussing today has to do with the limit of a collisional fluid, which we know is well described by fluid dynamics, hydrodynamics. And so then the conservation principles will determine how mass, momentum, and energy flow in the system, inside of the system, how things get redistributed. That's what we want to understand, how momentum and energy are redistributed in the atmosphere given the forcing. And also out of the system. That's basically what we're describing here. Now, something that may be obvious to planetary scientists and somewhat less obvious to astrophysicists is the fact that the fluid motion in that atmosphere are essentially thermally driven. By that I mean that they're driven by temperature differential. Let's say hotter at the equator, cooler at the pole. That's unlike many flows that are studied by astrophysicists. So maybe that's a point that you could see as a sideway, but I think it's worth mentioning in the sense that if you, I come from studying accretion disks around compact objects, and what drives everything that's going on there to leading order is a mechanical driving. So you have a Keplerian rotation flow, and you don't care about the thermodynamics to start with. Everything is driven, the motions are driven mechanically. If you want to form galaxies, large-scale evolution of the universe, same thing. Mechanics, gravity is what actually will drive the motions. Here, it is not. It's more subtle, because the thermodynamics of the system is actually has a strong effect on the motions, basically drives the motion, and it means it's a rather subtle system. So you have to account for the thermodynamics very, very carefully to get the fluid motions right. And so I thought that was worth emphasizing. So given all of these considerations here, then what people do to describe the atmospheric circulation of a planet typically is add a few layers of assumptions. In the same way we don't want to describe the fluid using Boltzmann equation. You just simplify things for yourself and you go from Boltzmann equations to the fluid approximation because the mean free path is small in the gas. Then you also want to try to find the leading order equation that are satisfied by the fluids without solving the full fluid equation. So you simplify the problem for yourself. And so the assumptions that are generally made, I think for solar system and exoplanet studies, are sometimes very good, sometimes might be worth reconsidering how good they are. But so the fluid is treated as inviscid, and an inviscid ideal gas. The stable vertical stratification implies that the horizontal motions dominate. So basically that's because you have if you have a stable an entropy distribution of entropy that is stably stratified, any vertical motion basically will be returned to any kick you give in the vertical will be returned to the fluid parcel will go back to its initial location. That's the meaning of stable stratification. So as a result, you are free to have motions horizontally, but not so much vertically. That's one way to think about it. And so you tend to have horizontal motion for that reason. And the other thing that is typically assumed as a simplifying assumption is that the temperature differentials are modest. If you look at the Earth, temperature from the equator to the pole, the differentials would be 10, 20%. That's a scale. So these are modest temperature differential. And they will lead to fluid motions that are typically subsonic. And so built in sort of the machinery of equation that we're going to see now, there is this assumption of subsonic motion. And you'll see that actually that breaks down for some exoplanets. Actually, that's one of the things I'll discuss towards the end of the lecture. And so what people have done for many decades is actually to get from the general fluid equations to a simplified set of equations called the primitive equations of meteorology. This was derived for the Earth, and it's pretty much valid for all solar system planets. And to a good extent, this equation should be valid to leading order for exoplanets, even though there are some areas of debate, I would say. And so basically what is done here is an approximation that, an approximate description of horizontal fluid motion on the largest horizontal scales. If you want to go on really, really small scale of what happened in this atmosphere, really, really, really small scale, let's say comparable to the vertical scale, these are not necessarily very good equations to use. Okay, so we are focused on the largest horizontal scale. And if you want to think about how you get from full fluid equations to this primitive equation of meteorology, in some sense, there is a semi-formal development in a small number, and the small number is the ratio of the vertical scale height to the horizontal scale. It's a small number, you develop your equation, and you drop terms that are small to second order, third order. That's basically what is done. This derivation is not trivial. I've looked at it personally. I don't think it's actually an easy derivation. It's well established, but it's not something that you do just in 10 minutes like this. It's pretty involved. And so let's look at this approximation that actually go into deriving the primitive equations. I'll show you the equations a little bit later. One of them is the assumption of hydrostatic balance. I took these words from a recent review by Kevin Heng and Adam Shulman, but you can find that in textbooks as well. So basically, one of the assumptions used here is the assumption that the fluid is hydrostatically balanced. And so you could read the text here. I guess one of the way to think about it that I like, because the same thing is done in accretion disks in astrophysics, is to say that if your horizontal motion are slow compared to the sound crossing time vertically, then it's okay to say, I filter out the short time scale out of my equation. I assume on the longer time scale, I always am able to reach hydrostatic balance vertically, and I'm left with slow motion horizontally. That's basically what you do. And so you force in the equation the fact that the fluid remains hydrostatically balanced. You also use geometry here. Geometry is sort of part of the argument as well here, because the sound crossing time is short because it's a sound wave just crosses this small scale height quickly. But you use another simplifying assumption, which is that when you have in the equation things, you use a reference radius r, then actually altitude, radial coordinate r in the equation is this reference radius plus an altitude z, and then you basically actually fix the radius to r itself. So you assume you stack up the layers, but they don't add up much in radius, so you basically ignore the thickness of the atmosphere, but you keep the derivative actually. So it's sort of non-trivial way of keeping terms, dropping terms. And then the traditional approximation might be even less intuitive. Again, I guess you have to sort of go through it to see how it works. But basically, you drop Coriolis and curvature terms that involve the vertical velocity, Vz. But the term involving Vz in the Lagrangian derivative here, the derivative following the fluid motion, this is capital D operator here, you actually keep the Vz term. So you see there is a fair amount of technical details here that go into what you keep and drop. I think the way to think about it again is that it's like a development in small number z over L, and then you want to keep only the leading order terms. And so when you do that for the Earth, it's not necessarily the case that it's going to be the same hierarchy of terms for hot Jupiter. So I think there is actually, it turns out to work okay, I think the primitive equation. But in principle, people could try to do that a little bit better for exoplanets. I'm not aware that people have really done that. Everybody uses the primitive equations that are valid for the Earth. And it's okay, but maybe not the best we could do in all cases. And so now looking at the equations to give a bit more substance to this, this is the exercise of going from Navier-Stokes equations to primitive equations of meteorology. So we want to express the conservation of momentum, mass conservation, or also known as continuity, energy, and then we need to plug in an equation of state here. So the equation of state is easy, ideal gas. This is actually turns out to be correct. I don't know of an exception for an atmosphere. So that's a pretty easy one. Conservation of momentum, oh, by the way, I should say that you have to do all of what I'm describing on the rotating sphere. Why do we do that? Because it's convenient to just be sitting, thinking of yourself as sitting on the planet and what do I see? So the description we have, and then we work in spherical coordinate, and then we sit somewhere on the planet and we look at the fluid on that point. That means we put ourselves in a non-inertial frame. So you do have to account for non-inertial forces in this rotating frame. So what you have then in your equation is a Lagrangian operator. So the acceleration following the fluid. This is a capital D operator here. You have here Coriolis forces. The other non-inertial term would be in that operator in this formulation. You have pressure gradient. You have, I guess we're assuming here it's a Newtonian fluid, which is an okay approximation. And so we have a viscous dissipation term here, another viscous term here, which might be related to bulk viscosity. Then we have gravitational acceleration, which is what stratifies the atmosphere in the vertical direction. And then you might want to add drag. Drag might be an internal form of drag, or it might be drag on the planetary surface. Continuity is just conservation of mass. And then energy equation, you might choose to express it as, I personally like to use entropy because I find it more intuitive. I don't like this PDV term. But in practice, people like to follow temperature. There might be numerical reasons why it's better to follow temperature, actually. And so what you have is temperature of the fluid following its motion. Again, the capital D derivative here is going to involve PDV term. So that's a sort of a weird form of the PDV term. And then heating rate here. I guess this Q here, the heating rate would be in Kelvin per second. You know, the unit here would be temperature per unit time. I'm going to have another Q later that's going to be energy per second. So that's why I want to specify this. And so you take these equations. You say the fluid is inviscid, so you drop viscosity here. I drop drag for now. I'm going to put drag back later on. So then I'm left with acceleration, Coriolis, initial term, pressure, and then gravity. And then all these terms I keep. Yeah? I think, yeah, it's hidden here in this operator, I think, in this formulation, yeah. Oh, that's right. So actually, yes, Dorian is right. The way you do it is that you don't use just gravity, you use a geopotential. And so that accounts actually, that's basically a deformation of this G. And then what you do is that you assume another thing that's done, I guess, that I can say now, is that you assume that we know rotating bodies, even rocky ones, are flattened, right? And Saturn is very flattened, for instance. So even though you know it's flattened, you solve it on a sphere or spherical shape. So again, it's an approximation you do there, and it's not too bad. But if we were to deal with very, very, very fast rotating planets, we might want to worry about also this approximation. Yeah. I'm not sure on top of my head. Is it? Okay, so it's a gas constant divided by the heat capacity, yeah. You'll see Cp appearing in the primitive equations, yeah. It's good to have an expert in the audience. Yeah. So then we get to the primitive equations, and let's describe this, the structure of this four equation, and then the terms, and then see what matters here. So we sort of split things in two parts. We had a momentum equation, momentum conservation equation that was in 3D, but because the vertical force balance is very different than the horizontal one, because we assume hydrostatic balance, then we split the vertical and horizontal. And so in the vertical, we just satisfy hydrostatic balance. It's expressed in a weird way. I'll get to show you how that works. And then the rest of the momentum conservation is expressed on the sphere here. And then there's a number of things I need to say. So you see, I need to apologize for the notation here. Now this little d remains a Lagrangian operator. So it's actually a full derivative following the fluid, okay? But I didn't have the equation written properly. So we're still doing things following the fluid. This is a term that actually is not necessarily too important. It's one of the initial terms here. I want to emphasize here, you might want to, for the sake of demonstration, I might want to say this one might be small. So let's not worry too much about it. I think that's generally true. Then pressure gradient, it takes a weird form, but that's a pressure gradient here. This minus grad P of phi. I also need to warn you that the little phi here is latitude. So forget about this for now. And then we want to focus on the big phi, capital Phi, which is a geopotential. And I'll explain exactly how that works in a moment. And this is a Coriolis force, a very important term. And then F is a Coriolis parameter. I'll get to describe the terms a little bit better. But basically, this is a momentum conservation in the horizontal, and it's done on pressure surfaces. So on top of things, what has been done here is that you put yourself on isobars. You follow the fluid motion on isobars. And that's actually quite convenient to do. You'll see why a little bit later. So that's hydrostatic balance. That's continuity. This divergence of here, you can, in fluid dynamics, you see that appear as a regeneration of PDV in thermodynamics. So that's what we're dealing with here. W is a vertical velocity. I should say the V here is a horizontal velocity only. So we describe the fluid motion in 2D, but on top of that, there is a vertical component that's typically much weaker than the horizontal one. It's part of the assumptions we have made. And then the energy equation now is written slightly differently. So you see the Cp appears here. Again, the PDV term is related to the vertical velocity. And my Q now is actually an energy rate. So it's energy ergs or watts. Ergs per seconds or watt. Basically, it's energy per unit time. That's right, yeah. Okay, so let's look at the term a little bit. The first one is I should define geometry. So it comes last in my list here, but K is just a geometrical unit vector that's normal to the surface everywhere. So that's to make sure you get the Coriolis term correct. And then the Coriolis term itself is this Coriolis, what's called Coriolis parameter, which is 2 omega sine phi, where phi is a latitude, 0 at the equator, plus or minus 90 at the pole. Omega is a rotation rate, angular rotation rate of the planet. So that's a Coriolis term, which you'll notice cancels out on the equator, as it should, because phi is 0, sine phi is 0, and then is maximum at the poles. Then what do I want to cover then? So that's pretty trivial. It's just acceleration. This pressure gradient here looks a little bit odd, and it is expressed in terms of this geopotential GZ. So the geopotential is simply the product of the gravitational acceleration times altitude above a reference level. So in your model, you typically you have some reference level, I assume a spherical shape, and then you describe the atmosphere as a function of altitude. So Z is the altitude. And then actually, because you do things on isobar, it actually makes sense to express the pressure gradients as basically difference in altitude of the isobars, basically. And then we will see that in that formulation, it's not, you don't want to think about the fluid motions being driven from a high pressure to low region. I guess you can do that. But another way of looking at it, I'll show that in a moment, is that it's simply the fact that isobars are generally slanted. So they're higher up where it's hotter and further down when it's cooler. And then the fluid simply slides down along the isobar, down the potential well. That's basically why you get winds. So I'll show you a picture of that. So it's a very convenient formulation to understand why you get winds. I find it very intuitive, why you get winds in the first place, if you have a non-uniform temperature. So it gets time, it takes a bit of time to get used to this equation. It's really different. If you come from fluid dynamics, it doesn't look like familiar, but everything is working as it should. What else do I want to emphasize? I guess that's all I want to say on these equations. If you have a question, I'm happy to take a question. I should say this is what is solved. As far as, this is what is solved when you want to do meteorological prediction for the Earth. This is what is solved when you want to do climate. And this is what many people have adapted to solve for exoplanet climate and circulation. Yeah. No, QG equation is a reduction of this, I would say. Would you agree, Dorian? Yeah, so QG is quasi-geostrophic. So the point is that, you see, Pascal, this is Coriolis term, this is pressure gradient. when you want to focus on geostrophic balance, you actually, these two terms are dominate. And so, and there is more going on in getting the QG equation. So, but I think the short answer to your question is QG is a subset, is a simply a focus. I don't know how to say it. It's just a special case of those equations, yeah. Yeah. Yeah, so you do have to actually map one to the other. So sometimes you do have to integrate vertically the hydrostatic balance to know where you are in the solver. Yeah. And that's dependent on the temperature structure of the atmosphere. Yeah. So you may need to have to do that frequently in your solver. Yeah. Any more questions? Okay, so let's go back to our sort of basic ideas here. We have seen the equations. We can go back to consider a bit how we might want to use them to describe the atmosphere. So we are again dealing with this thin film layer, finite mass. It exchanges momentum and energy with its boundaries. What is generally done, and is generally So this gets to be a bit technical. My answer to this, which is more in the section about solvers, is that people have found, as far as I know, and maybe Dorian and other people might comment about this, if you had a perfect solver, you would actually satisfy perfectly linear momentum conservation, angular momentum conservation. In practice, when you code it, let's say you finite difference it, there is an issue. You have to make choices about what quantities you conserve. And so people might say, I want to conserve angular momentum. I feel it's really important. But then I might not conserve this other quantity that's entropy that's actually really important for turbulent cascade. And then other solvers might go and say, I really want to conserve entropy, but then I have to drop the conservation of angular momentum. So my understanding is that at the solver level, when you code this equation on the computer, there is no, as far as I know, and I can stand corrected, there is no solver that guarantees both the conservation of angular momentum, which makes sense to me intuitively, but there are other quantities that are really important to describe the turbulent flow in the atmosphere, and then you have to cut on some corner. Do you agree with that?
Yeah.
Okay.
The term, you mentioned the term you can be there.
Yeah.
And that it's not that important. And if you want to do angular momentum conservation,
So that there are actual terms that directly affect the momentum. For example, the tidal torque directly affects. There's no sign.
But what do you mean by tidal torque? The torque on the atmospheric mass?
The moon has a tidal torque.
Yeah, so the way, yeah, but the way, you can add terms. You can add terms, yeah. So for instance, we might add some drag. So the way you would do it is adding terms. In fact, I have recently worked on this problem of atmospheric tides on exoplanets, and the way you do it is add some terms, yeah. Not necessarily easy, but that's the way you would do it. You would say, I have a gravitational pull on this mass element, so let me add that force. It's an external force, yeah.
I think that in terms of the solvers, respectable and usually are good at doing momentum conservation. Finite volume ones are better at doing
Okay, so what is generally done then is that you assume mass is constant. In fact, some of these solvers, to go back to this question, don't conserve mass. The spectral solver that I'm aware of and I use, they actually don't conserve mass perfectly, so every time step you adjust the mass. So things are not perfect, if you will, but it turns out not to be a major problem. The assumption of mass conservation makes sense from the following consideration, that there are things that are changing. Certainly, in the Earth's atmosphere, there's water coming out, there's CO2 coming out from volcanoes, so that is changing. But the times, and then some of that can just go back in the Earth's interior. Also, for exoplanets, something that's quite relevant is the fact that you can lose your atmosphere. But those timescales, millions of years, billions of years on which this process happened, are really, really long compared to the atmospheric circulation timescales. So in fact, it's a good approximation to say it's a finite mass layer. The angular momentum, well, simply said, if you're just looking at this fluid layer, and then it's isolated from what's up and down, then you have to conserve angular momentum in that fluid layer. When you put that fluid layer on top of a rocky surface, then actually there is drag at the boundary. And so effectively you can deposit angular momentum from the atmosphere in the bulk rotation of the planet, and the bulk rotation of the planet through drag can actually provide momentum or take momentum away from the atmosphere. And so effectively that's treated as it's known as a planetary boundary layer problem if there is a solid surface. And that is sort of understood. You can think of it as in first approximation, it's from the point of view of hydrodynamics, I would say it's a no-slip boundary condition. You know, the fluid is flowing on a solid and is not allowed to slip at the boundary. But this is not that simple because actually the fluid generally becomes turbulent there. And so actually what people do then is that they borrow the extensive understanding of turbulent boundary layer that comes from fluid dynamics and a lot of engineering, I think, and they prescribe a subscale description of the turbulent boundary layer and how you get effectively to exchange momentum, heat, and water vapor, say, from your surface all the way to the bottom layers in the atmosphere. And this is, from the point of view of an astrophysicist, I'd say this seems to be a relatively well understood part of this problem. So it's subgrid physics, but it's relatively well understood. I'll point to you, and you see later, that when you are dealing with a giant planet now, or actually even a planet, but let's say a giant planet with a thick atmosphere, one of the issues we have is that we don't know exactly how well to define our bottom boundary and what happens at the boundary. Because there is really fluid down there, but we cannot describe the whole planet. So this is one of the lecture 3 open problems that I mentioned. Yeah? Sorry? Yes, so that's right. So on the larger scales, the fluid is actually inviscid. On small scale, actually there is viscous behavior, especially close to this boundary layer, but it's even more complicated than this. I was not going to mention this, but something that's key, we know, is turbulence. So you get 2D turbulence. Okay, so I didn't have a slide about this, but I can mention it briefly in words. That's what astrophysicists do, and it's not a bad start. Is it just say, I have viscosity, but it's so small that let me treat the fluid as inviscid. But it always comes and bites you because the fluid needs a way to dissipate somehow. And so the way it's done in atmospheres is actually to describe the fluid motion from the larger scales to the smaller scales you want to describe. You don't want to go to too small scales because maybe your equations break down. So you have some scales, some dynamical range of scales, and at the smaller scales, you want to dissipate the motion there. And the thinking here is that it is, again, a sort of a subgrid treatment of what some turbulent dissipation and cascade going down to smaller scale might do. Things get even more complicated in atmospheres because on the larger scales, the flow is 2D, as I was mentioning, and actually you get an inverse cascade. You get energy to go to the larger scales. So I don't know what my short answer to your question would be, but basically in the solver part, people do include viscous terms, and they are not physical viscous terms. They tend to be iterated viscous term, high order viscous term, so that you only dissipate flow motion on a small scale. And that's an effective way of accounting for the fact that the true fluid is actually not inviscid. There is some finite viscosity. Yeah. Oh, okay, you correct me if I'm wrong, but I was just referring to the problem of the planetary boundary layer. That part, which is the friction on the solid surface and actually how you affect the exchanges between the atmosphere, the bottom layer of the atmosphere and the surface. My understanding is that this is relatively, and again, my point of view is that if you do things at the 10% level, it's good. So you have to understand that I have this like room for space that I allow myself, right? And so at the detail level, it might not be satisfying. I understand that. Now, what you're referring to, or what I was talking about at least lately, is the issue of the internal friction away from the boundary, if you will. And that, I take your point is well taken, that I think this is a tricky business to treat well. People are satisfied with this, well, I don't know, maybe some people are not satisfied, I should say, with the fact that you have this treatment of the dissipation on small scales. But certainly something I've seen myself is that the result of your simulation, the wind speed, for instance, and other features are affected by how much of this distribution you put. So then you don't like that because you have a free parameter and you want to get rid of free parameters as much as you want. So certainly there is actually room for improvement there. I don't know if it's if what you meant.
I'm not an expert in math. The incorporation of parameters or sub-rescale models very, very
Okay, so maybe. Okay. I was under the impression it's not a huge problem, but maybe I'm wrong. Yeah. There was another question or comment here? Did you have you raise your hand? No?
I was just puzzled, yeah. Maybe, I gather that, so you have a grid scale that has some description, but there was many, an instrument cascade that's going on a grid scale, so the instrument
Yeah, correct. Energy goes upscale, and then entropy goes downscale, yes. And then the true atmosphere, of course, is 2D on the larger scales, but transitions to actually being 3D turbulence on smaller scales. And so, but generally speaking, we only cover the 2D part of the spectrum in simulations, I think. Yeah. Yeah, so that's so we're getting a lot in the numerics, which is sort of at the end of the show. But there are some choices there. What I'm familiar with is just a zero pressure boundary layer. But there is some trickiness in this because then you get the waves to be reflected. So you get the picture here. I don't want to get too much into the details, but you can write down the equations. In practice, when you put them on the computer, you run into a number of issues to do things well. And so the upper boundary condition can be actually a problem. So people then get to put sponge layers, which is an absorbing upper layers. And all of this is some tweaking involved. And there might be a better way of doing it. That's what I'm familiar with in the codes that I've seen. Yeah. Maybe, yeah. Okay. The other thing that I'll mention here is the business. So the problem of, well, I was discussing, again, this general description of the atmosphere. In terms of energy, the dominant term that you want to make sure you capture well is radiative forcing. And specifically the fact that you deposit some energy in the atmosphere itself. We've heard about, like, for instance, this temperature inversion in the stratosphere. And the fact that you hit some region of the atmosphere more than others, for instance, the equator versus the pole on the Earth. And so that is actually the key driver of atmospheric motion. One thing that is less often mentioned, but is of interest, is the fact that there will be friction in the fluid. So for instance, we discussed a cascade. When you dissipate energy on small scale, there is some friction involved. When you have a planetary boundary layer, certainly you drag, so you reduce the momentum of your fluid, but you also get rid of some of the kinetic energy. That's what viscosity does. And so there is some friction involved. And so you heat up the fluid. And naively, you might think I can just not look at this. But because your atmospheric motions are driven by thermal effect, you want to make sure actually it's okay to neglect that. And so at least one result I know, I've seen discussed for the Earth, is that we know the answer. The friction the heating from friction in the Earth's atmosphere never account for more than a few % of the radiative forcing. So it's okay to run a model for the Earth and saying, I don't even conserve energy exactly. I just the friction. I get to lose some energy because I don't. The rate at which I apply friction in the fluid should be returned as heat to the fluid, but I don't do that. That's okay. You still get a good answer. This is not necessarily the case, though, with exoplanet atmosphere. We have to be careful about this. So one of the themes that you'll hear from the lecture is that friction might be actually a big thing for us to figure out, as much as we can. It's a difficult thing in some cases to figure out. And so the dominant term there is a forcing, and that's all the business of doing the radiative transfer properly. Yes. So, okay, you'll see a little bit later in my slides. Basically, I think we do not understand the friction in the solar system giant planets. And the friction is actually a serious problem for many of the exoplanets, understanding it. We might have one good candidate, I would argue, and I'll develop this argument through my slides. But friction is actually something that we want to understand as much as possible in general, and it's not an easy business. Yeah. So even solar system, there are open questions. You'll see how that plays out. So how do you get to the atmosphere to flow? Well, I think the simplest way to look at it is this picture here. So first thing I need to remind you of is that you do hydrostatic balance. Then the scale height, the E-folding scale height for the pressure, is actually the gas constant R times the temperature divided by G. Actually, that's maybe for an isothermal atmosphere. I'm being loose here. The point is that the hotter you are, the larger your pressure scale height. So now, what that means is that if I shine more, receive more insolation at my equator on Earth and less at the pole, then I don't have actually, relative to a reference radius, going up in altitude here, I don't have actually, if you will, flat isobars. I have them slanted. The pressure scale height at the equator is larger than at the pole. So my isobar is not at a given altitude. It's actually slanted higher up at the equator and further down in altitude at the pole. And so my fluid then naturally will want to go down on this, because it's flowing on isobar. I show you the equation for the primitive equation of metrology. It's just going to go down this slanted isobar towards the coolest region. So the hot fluid will go towards the coolest region. And then it's going down the potential well. Because remember that my geopotential here is GZ. I'm going down in altitude. Therefore, I'm able to transform. So it's just like a simple mechanics problem. I'm able to transform my potential energy going down the potential well into kinetic energy of the wind. It's really, really simple, I think that way. You basically go down slanted isobar and you accelerate the wind. That's what drives motion. If you have uniform temperature, you then have equal altitude isobar. There is no motion a priori, at least no motion driven that way. And so, great, this is how we accelerate winds. This is how we get winds in an atmosphere, just going down this slanted isobar from temperature differential. But then we have to understand what limits this acceleration. And this is where friction comes into play. So we're going back to what we were just discussing now. Friction, some form of friction, will actually limit this wind acceleration process. And the other thing that happens could be tricky is the fact that from the friction you heat up the fluid, and so you can actually change the shape of the isobar locally. If locally you have a lot of friction, you can change the shape of the isobar, and so you accelerate, you dissipate some of the wind kinetic energy, you change the isobar, and the forcing itself is changed. So it's a strongly coupled problem in the sense that fluid motions depend on the thermal state, but because the wind themselves are subject to some friction, they have to, otherwise you would get infinite velocity winds from this process, if you will. The wind itself is feeding back on its thermal forcing. And so what we generally want to understand to say that we have some understanding of the circulation in an atmosphere is that we want to say we understand the forcing and the friction. Because this is what ultimately will set the wind speed in an atmosphere. And the forcing, we actually understand it relatively well. So the geometrical shape of the forcing, let's say more insolation at the equator, less at the pole on Earth, we have a good handle on that. And same thing for, let's say, hot Jupiters. If you think there is permanent day side, permanent night side, you have the geometrical shape, you know the fluxes. So we generally are able to describe the forcing well. And so what we're left with is actually understanding the friction. And so I think that's a significant open problem here that I'll explore further in the slides. In other words, if we want to understand what sets the wind speeds, we need to understand what's the leading friction mechanism in a given atmosphere. Question? Yeah, that's right. So it's true, actually. It adds up. It should be more slanted here and even more slanted there. Correct. Yeah. And so that's one of the reasons why you get so high speed in hot Jupiters high up in the atmosphere, because the slanting adds up. Yeah. So what sets the wind speed? Let's just explore that a little bit more and maybe come back to it later. So it turned out that it's a challenging problem. So going back to your question, it is a challenging problem even for solar system planets. So my view on this, and I welcome comments from experts or people who have maybe additional knowledge on this, is that, again, the forcing is relatively well known. And what that means is that we can treat the relative problem in the atmosphere relatively well. And so we know what forces the atmosphere. The friction on terrestrial planets, I think, is also relatively well understood. And so someone made a comment about this maybe not being the case. I suppose one way to look at this totally empirically is that if you take a GCM for the Earth, a climate model for the Earth, start at rest and then spin it up, force the atmosphere relatively, and then ask what sort of wind speed you get, now Earth GCMs do a pretty good job at getting the wind speed right. They might not getting at the 1% level, but certainly at the 10% level, it's easy. And so that means you get the forcing and the friction through the treatment of the boundary layer okay. There's probably room for improvement, but we do have a handle on the forcing for the Earth that's decent. Whether that carries over to other planets, even other solar system planets, is something I'm not sure, because it's true that the regime of boundary layer could change depending on from planet to planet. But what's nice is that you know, presumably, what's the dominant friction mechanism, that it is this planetary boundary layer, because you have friction on the solid. So that must be the limiting factor for the winds. And I think it generally is. Then we're in trouble when you go to gas giant planets, because there is no solid surface. I mean, surely there is a core, but it's so deep that probably it's totally decoupled from what happened in the atmosphere. So we get to accelerate our winds on the giant planets and not necessarily know well what limits their speed. And it's non-trivial. We know it's not trivial for the following reason. A simple example from the solar system. Neptune receives only 4% of Jupiter's insolation. Its wind speed, sort of average in some global sense, amount to about 200 meters per second. Jupiter's wind speed amount to about 40 meters per second. So clearly, Neptune is forced very much less than Jupiter, and yet it is achieving much higher, 5 times higher wind speed. So clearly, what is playing here is different friction. It has to be. I have much less forcing, and I achieve much higher wind speed. It must be because the friction is much less. And there are similar planets. They are gas giants. I'm not changing dramatically anything. So this is a subtle issue. Okay, but that is not a convincing answer to me, I'm afraid. I mean, you may have something in mind, and I'm happy to hear about it, but I want. So what would be nice, and people have struggled with this, is to run simulations for the giant planets in the solar system and diagnose them and see where energy flows until you can understand the friction. If you get the wind speed right, maybe you need to put extra physics to even get the wind speed right. And this is still not a solved problem for the solar system. This is what I'm trying to bring up. So when we do extrasolar planets, caution. Because if we don't understand the friction, we could be wrong by a lot. That's, I guess, the message. Yeah. Yeah, that's a good question. So I was going to avoid that area altogether because we tend to deal with strongly irradiated planets. So then, yeah, so that might play a role. That's right. Yeah, yeah. The point that maybe I swept under the rug is that the internal flux is a non-negligible contribution. In fact, for Jupiter, it's about equal to the irradiation. And so this actually is another additional form of forcing that actually plays a role. And so the difference between Jupiter and Neptune that way may be a difference in forcing that's just beyond this 4%. That's correct. Yeah.
Well, the internal energy or the scale, neither of those are future solutions to this problem. It's not just Neptune and Jupiter, it applies to Earth, Mars, Jupiter, Saturn, and the isoplanets. As you go out, the characteristic density increases. So the Earth might be 30 meters a second,
Yeah.
Mars 80 meters a second, and then Jupiter. Talking about the jet here, it would be like 100 up to a few hundred when you get to Neptune. So less insulation, but as you go out, just less puzzle. And it's not solved by I haven't observed the error bar, and that's also biggest on Saturn. And some of these planets like Mars and Earth are similar scale. So it's a bit of a paradox to resolve.
It's an unsolved problem, even for solar system planet. Yeah. But my impression was that we're in better shape for the terrestrial planets because at least there you have this boundary layer that actually is dragging the flow, and the treatments do give you decent wind speed for Mars, Venus, and the Earth. Any more comments or questions? Okay, so the other thing that is worth discussing briefly is sort of features of the flow we might expect. Whenever you have a new set of equations in physics, what you should do is linearize them and perturb them so that you learn about the wave modes that are dominant as an emergent phenomenon in your fluid. And so you can certainly do that with a full fluid dynamics equation, but it's actually more useful to do that just with the primitive equations because they are the equations you're interested in. And so there's many type of waves in an atmosphere that are possible. I'm just highlight two of the, I think, most important ones that are known to play a role in atmospheric dynamics throughout. And so the first one is gravity waves. And basically, the way you want to think about this is this process I described already. If you have a stably stratified atmosphere and you push a fluid parcel up, then because the entropy stratification is stable, you're going to return that fluid parcel and it's going to oscillate. And now you get coupling within the various layers of the atmosphere, so you get a vertically propagating gravity waves. The way you want to think about it is it can be very slanted, right? It doesn't have to be strictly vertical. So basically, these are vertically propagating sound waves, and the restoring force is a vertical buoyancy. They are related to what in fluid dynamics is generally known as internal gravity waves. So it's the same type of waves. G waves in stars. This is the same type of waves. And they play a role, an important role, you can imagine, in the vertical couplings of the various layers, and also are strongly associated with a problem known as the Rossby adjustment. I don't know if I'll discuss that too much later in my lectures, but it's words that you might hear about. So as a guide, I have them here. And then the other type of important waves that you see emerge quite frequently in an atmospheric flow are Rossby waves. And you probably want to think of those, they are horizontally propagating waves. The restoring force here is the Coriolis force. And the meaning of that, you might remember that from simple mechanics, or you might know that, and it's great. The Coriolis force is nothing but an expression of conservation of angular momentum. So if on the sphere you try to displace a fluid element away from its latitude level, up or down in latitude, then by conservation of angular momentum, you would have a tendency to go back. And then you get an oscillating wave that travels, actually, along the latitude circle. And so these are basically what Rossby waves are. And they play quite frequently a role in the horizontal flow. And also, they can be important in describing the two-dimensional turbulence. And there's probably other applications here that I don't have in there. And so I thought I would just show you graphically what they look like. I'm not sure they're even scientifically valid pictures, but they get the message through. You see this, if you see a flow pattern of, so if you think the wind speed, it's a wind band like this, oscillating around the latitude circle like this. I think this might be actually real coming from a polar vortex interaction. I'm not quite sure, but anyway, this sort of pattern like this that's emphasized in color, that's typically a combination of Rossby modes, Rossby waves. And then just one way to get gravity waves is not the only way. You don't need to get mountains to actually get gravity waves. You'll get gravity waves in your flow in general, but a nice way of driving them is to get a flow above a mountain. So you get this bottom layer to sort of go up, and then effectively that's a way of triggering this vertical motion that's actually propagates vertically. So that's just a nice simple example of what a gravity wave might be. And so again, they play a very important role in atmospheric circulation. Another thing that you want to pay attention to when you have a new system of equation is not just a wave response. Sometimes you do a perturbation and you find that actually it's not stable. And so instead of a wave response, you get an instability. It's very general. And so there are a number of instabilities that are important. I actually happen to think, again, in this last lecture, I don't know that I'll say too much about this, but I happen to think that in the exoplanet context, we have not gone through all the relevant instabilities, maybe. There is interesting things to probably be figured out because the physical regimes are quite different than what we know in the solar system. But so the two main instabilities that are discussed in the atmospheric dynamics literature are the so-called barotropic instability and baroclinic instability. The barotropic instability, you want to think of that as a horizontal instability. I guess I should be a bit careful here. It's a shear instability. And then a shear instability can be actually affecting a vertical profile with shear or a horizontal profile with shear. But because we have filtered out vertical motion in our primitive equations, with the exception of what's required to satisfy continuity, we are not able to actually, we're totally unable to describe modes that could be driven by strong vertical shear. So if I get two layers stacked on each other with very different horizontal velocity, the real fluid system might be unstable, but my primitive equation will not find it. That's one of the reasons why people add this eddy diffusion you've heard about yesterday, is that you do not describe that in a GCM with the primitive equation, so you need, if it's present, you need to put some turbulent mixings by hand. What I'm referring to here is the same process, but horizontally now, and I'll show you an example again. If you get strong, let's say an equatorial wind going eastward, and then actually strong shear going westward, a little bit away from the equator, that's a strong shear horizontally, that can break into turbulence. It's a shear instability, and so you might hear that referred in general fluid dynamics or in astrophysics as Kelvin-Helmholtz. In the atmospheric dynamics literature, it's called a barotropic instability. And so the way you want to think about it maybe is that if you've looked at a little bit at this in the general fluid dynamics literature, there is such a thing called the Fjordhoff criterion. It's an inflection point criterion. So it depends on the shape of your velocity profile, and if you get a second order derivative with an inflection point, then you get actually to be unstable. But you have to do that on a rotating sphere. So the barotropic instability is nothing like the regular shear, as far as I know, as I understand, it's nothing like the regular shear instabilities done properly on the rotating sphere. Baroclinic instability is actually, to me, the most intuitive way to think about it is a form of slanted convection. So convection happens if you have strong, the regular convection, let's say of stars, when you have a lot of energy production from nuclear fusion, you actually, opacity changes in opacities that are significant, say, you basically set up an entropy gradient that is unstable. And another way of thinking about it is that if you get too steep of a temperature gradient, you actually you lose your stable stratification, and you get to favor energetically vertical motion. So in such an atmosphere, when I displace my fluid element up in the blob picture, it keeps going up through buoyancy or going down through buoyancy. That's basically what convection is. Now, when we do that in vertically, the sort of assumption we have is that everywhere horizontally the temperature field is the same, which is a good approximation for stars, say. But now in atmospheres, we've seen that we generally, because you shine on an atmosphere, you generally will have hotter region horizontally and cooler region horizontally. And so it is possible for you to find a mode of slanted convection, where you don't do a vertical displacement of the blob, you do a mix of vertical and horizontal displacement of the blob, and you can find some actually wave vector, some direction for this mode that actually is unstable in a slanted way to the same convection principle. So that's my attempt at explaining what baroclinic instability is. On top of that, you have to do that on the rotating sphere. But that's basically baroclinic instability. Yeah. Correct. So another thing that it does. It's a matter of time scale. Well, maybe someone can express a different point of view, but it is correct that you vertically you assume a hydrostatic balance, and so effectively, if ever in a general circulation model you find, and you have to test for that, or your run will crash, basically your model explodes. If you ever find that a column is over some scale height unstable to convection, what you do is that you quickly correct it to be marginally stable. And the reason you do that is separation of time scales again. Because you see, convection is generally a fast process, a turnover. So basically you say, if there is convection acting, it will act on timescales much shorter than the timescale on which I follow the atmospheric circulation. And so I just correct it to marginal. So every time step you go and you correct all the columns that are convectively unstable. Because if you let them be, there is a problem in the formulation that you don't account for that. And as far as I know, the code crashes. Yeah. And so baroclinic instability, I think the point here is that it occurs on a slower time scale. And so you are able to follow it. But I'm not sure my answer is ideal, because I see your point is that it's a form of slanted convection, so why is it that it's allowed while the others are not? There's probably a better answer than mine on this. The fact is that it's well followed by this, I'll show you an example. It's well followed by the solvers, yeah. Did you want to say something, Dorian?
Well, I was thinking it might have to do with, larger scale. Convection is something scale.
So it's yeah. Yeah. Yeah, I see your point, yeah. So it's a slower time scale, but also the fluid equation, the primitive equations are satisfied to leading order on the larger scales. So actually, and baroclinic tends to develop on the larger scales. I mean, it's possible that there are smaller scale instabilities. So again, it's going back to my point that are not described by the model, and then the issue being just horizontal scale not being described. That is also a possibility. You could think of very small scale baroclinic instabilities that are not described because they're below the grid scale of your model. That is a possibility in principle. Yes?
When you're following something like baroclinic instability, are you able to see it at some horizontal motion and then have that balance compensating for the slant part? How do you see it? I understand why it might happen because it's not slow.
So you can do the linear theory of it. And you know the gross time scale, you know, there's extensive literature on this. It's really well understood for the Earth because it's a dominant process for headless cell driving the jet streams. Okay, so it's really well understood for the Earth. And so you know, given the condition in your atmosphere, you know the gross time scale, for the fastest growing mode, you know the physical scale, you know the wave number along the equator. You know that you should get about these 6 modes or 8 modes. You know everything. You just put it on the computer and you get the right answer. So people are satisfied. They know what's going on. And I'm sure you can diagnose the hell out of it, okay? So you sort of know it. You recognize it from linear theory. And then it breaks down at the nonlinear stage, into various modes and waves. But it's well understood. Yeah. Does that address your question?
More of a comment on how to get convection.
Yeah.
Comment maybe to help out is I think the large bouncing from a large scale, level scale, thousands or more kilometers, where do they want to not scale? Where protection happens, when we told you about protection, it's small scale adapted on a scale of a horizontal scale of 100 meters, maybe a kilometer or something big. And in web forecast model, the big scale will be in the tens of kilometers, hundreds of kilometers. So protection is always needed. What we're talking about protection, not the scale process, which can't be resolved, whereas the parasemic stuff is optimized many grid scales as well resolved, and you see that in web.
So I think I'm going to have to finish with this slide because we're getting... No? You want I go to 20?
Yeah.
Okay. Okay. I mean, there's a lot of questions and comments. That's great. Okay, so let me just show you some examples of these instabilities. Some from my own work and some from recent interesting work actually for hot Jupiters. So when you want to use one of the circulation models for exoplanets, you need to make sure you have put it in such a way that you can reproduce the Earth at a decent level. So that's one of those simulations here. And on the Earth, you do get baroclinic instability to occur at mid-latitude. That's a consequence of, well, one way to think about it is this business of Hadley cell that I won't discuss too much, but you want to think about this meridional circulation that's trying to bring the hot flow from the hot gas from the equator to the pole. But because of Coriolis effect, you actually are limited in how far you can go in latitude. So you create strong temperature gradient at mid-latitude, and actually those temperature gradients are baroclinically unstable, and then you see the development of that baroclinic instability at mid-latitude. And that actually then subsequently lead to the formation of the jet stream. So this is again Earth-specific. I mean, the process could happen on an exoplanet, but the Earth is a test case baroclinic instability problem. Barotropic instability is maybe a bit less obvious. And so early on when I started modeling hot Jupiters, I seem to have found actually some case of simulation. They were specifically very shallow in depth, where the flow seemed to violate this barotropic instability criterion, the one that I mentioned, the inflection point. And then it would break into this oscillating, what looks like Rossby wave modes, and with a lot of variability. But since that, the deeper model didn't show that. Since that, many simulations have been done, and they have not reported anything like this. So I thought, I probably did something wrong. But actually, this year, just a few months ago, Sébastien Formin and collaborators, using a full hydrodynamical model, not on the sphere, but a beta plane, so it's an approximation of the sphere, I've reported for hot Jupiter simulation also seeing actually barotropic instability developing. So you see you get these very well-aligned jets going along the equator like this. You'll see that's a standard result for hot Jupiter. That actually starts to oscillate and drive variability in the flow. So that may be an example of us having not figured out everything about what's going on in some of these atmospheres. And I guess the general point that you might want to take with you is that figuring out whether you get one of these large-scale instabilities to happen is important, because observationally they will generally lead to quite a lot of flow variability, and you might see variability then in the planets you're observing. And it's 10:20. Okay. Let me see what. Well, it's sort of a good time maybe to break, because it's a bit of a long discussion there. So the next thing I want to do tomorrow, to have a number of things I want to address, but this is another useful way of looking at a flow is dimensionless numbers. and because they can characterize the flow dynamics, the regime at least, and it's quite useful to understand what happens in some of these simulations. I think I'll stop here for now and take more questions if there are more questions.